Now, let's have a look at some more simple harmonic motion problems. So, the first one here we want to show that something's moving in simple harmonic motion. And it starts with a displacement of 7 cos 5t, and we want to prove that it can come down to minus 25t, which is in that simple harmonic form. Remember, minus n squared x. So we can get it back as in terms of its displacement with a negative out the front and some number. So the negative 25, obviously. So 7 cos 5t can differentiate to minus 35 sine 5t. Remember, cos goes to negative sine. We've got here, and then multiply by the 5. 7 5s are 35. And then multiply by 5 again gives us minus 175. Sine differentiates to cos, and the 5 multiplied out. So we can separate that to 175 is 25 times 7. And so 7 cos 5t is our displacement. So we get minus 25 times displacement. So that means it is in simple harmonic motion form. So then we want to find the times at which the particle will have maximum displacement and find the maximum displacement. So there's a few ways we can do this. We know our maximum displacement will happen when v is equal to 0. So if that's the case, set v is equal to 0 and solve that equation. Sine of 5t would be equal to 0, so 5t is equal to n pi, or the time would be n pi times 5. So they're the times. So again, we've just solved and got a formula function that will allow us to get the general solution of that sine 5t is equal to 0. Notice that n is a non-negative integer. So we have that situation. And then from that, we can find our maximum displacement by really just looking at the function. Cos of 5t is going to be between minus 1 and 1. So the greatest value it's going to get is 1. The smallest value is minus 1. So its maximum displacement would be 7 units. Because we know it's moving around the line x is equal to 0. So point x is equal, that's its center. Question 3. Particle moves in simple harmonic motion, and it's given to us by minus 16x. So show that the placement of the particle given by 3 sine 4t satisfies this condition. So again, start with 3 sine 4t, differentiate 12 cos 4t, and then differentiate again, gives us minus 48 sine 4t. So we're just differentiating cos 4t and some sine 4t, the cos 4t, and we're able to get minus 16 times 3 sine 4t, which gives us minus 16x, which we wanted. Find the time when the particle is first at rest. Well, when the particle is at rest. So again, we take our first derivative, which is a velocity, set it equal to 0, and we get cos of 4t equals 0, or 4t is equal to inverse cos of 0, which we would get as a general function of 2n minus 1 times pi on 2, and divide by 4, so 2n minus 1 times pi on 8. So we're getting the odd functions there. So we're either at the positive or negative y-axis, and then find the displacement and acceleration at these times. So again, we can look at the idea. So there's that function again. If we wanted to look at that way, we can look. There's another way of looking. 4t equal inverse cos of 0, which is 2n pi plus minus pi on 2, which we can get time being exactly the same. Displacement at these times, well, again, what's our greatest displacement? So we know when it's at rest, we're going to get the maximum displacement. Sine of 4t is between minus 1 and 1. So that's going to give us 3 lots of 1. So maximum displacement is going to be 3. Acceleration, again, well, when x is equal to 3, what's our displacement? We got back to minus 16x. So it's minus 16 times 3 is minus 48. So vice versa, like when it's minus 1, it'll be a positive acceleration. When it's positive, that works out to be positive 1, it gives us a negative displacement. So we're able to see that the acceleration will be 48. This time we got x equals to 2 cos t plus pi on 4. So our curve's been shifted across. Show this in simple harmonic motion. Well, again, get our derivative. We get minus 2 sine t plus 4 pi on 4. And our acceleration is minus 2 cos t plus pi on 4. So notice the 2 cos t plus pi on 4 is the acceleration. It's in the form minus 1 squared on x. It's acceleration in simple harmonic motion because we can put it in the form minus n squared on x. What times does the particle be at the origin? So we set it up and set the function equal to 0. So cos of t plus pi on 4 is equal to 0. Again, our general formula would be 2k pi plus pi on 2, where k is going to be a positive integral. So we can get times of 2k pi plus pi on 4, 2k pi minus 3 pi on 4 with that. So we're doing positive, adding and subtracting there. So that will be our time. So when we've got t plus pi on 4, pi on 2, 3 pi on 2, gives us t of pi on 2, 5 pi on 2. Write down the period of the motion. So period's going to be 2 pi on n, and if our period value of n we got from our acceleration, because that's the value we can put in for n there, it's 1, so our period is 2 pi. And find the maximum displacement. So again, the cos t plus 4 pi on 4 is going to be between minus 1 and 1, which means the greatest displacement it's going to get is 2 units away from the center. So it's not too hard to get that one. This time we got the velocity of a particle that's moving in simple harmonic motion is given to us by this function, v squared minus 4x minus x squared. Find the 2 points between which the particle is oscillating. So if that's the case, if it's oscillating, it changes direction then when v is equal to 0. So if we set it equal to 0, then we get x being outside of 4 minus x, we get 0 and 4 being our values of x, between which it's oscillating. So it's starting there at 0 and moving to a point at 4. And it's because of simple harmonic motion, it'll move backwards and forwards between those two. So our center of the motion, well, center between 0 and 4 is 2. That's not too hard to find. It's because it's got to be right in the middle. Find the maximum speed of that particle. Well, the maximum speed there, which we haven't got. There we go. There's our maximum. We know at the center the velocity is going to be a maximum, because we know simple harmonic motion moves between 2 points. At the end points, it's 0, the velocity is 0. In the middle point, it's going to be at its fastest. So at x is equal to 2, we get the speed of 2 meters per second. So, and we notice we said speed. We didn't say velocity. It's speed because obviously if it's moving in that direction, the velocity is positive. It's moving in that direction, the velocity is negative. So we're really looking at just speed, because at that point it's 2 meters per second going in either direction. And then find the acceleration of the particle in terms of x. Well, we go back to the work we've done before when we've got the acceleration in terms of x. To start with velocity squared, well, we need a half velocity squared to differentiate. So we take half of the function there, so half of 4x gives us 2x, half of x squared gives us the half x squared. Differentiate that with respect to x, gives us the d dx of a half v squared, which is acceleration, which gives us our acceleration function as 2 minus x. So we were able to get it there, and then we notice we can start to play around and look and go, well, we know when our acceleration is 0, we get x is equal to 2 meters. So that works out because acceleration at the center of the motion is 0. So that confirms it for us, that must be the way to go. And question 6, the weight of the is suspended from a spring. It's pulled down to its maximum displacement of 9 centimeters and let go. Acceleration is then given by that expression there. Find the equation for this velocity in terms of x. Well, again, we start off with instead of taking acceleration in this form, we'll take it as d dx of a half v squared, because it's minus 1 on 9x. So we integrate half v squared is equal to minus 1 on 18 x squared plus c, and we know when it's pulled down to its maximum displacement. So it's not actually moving, but its position is 9. So that allows us to get our constant of 9 over 2. So a half v squared equals the minus 1 on 18 x squared plus 9 on 2, multiply through by the 2, and we get the velocity being plus or minus square root of 9 minus 1/9 of x squared. We say plus or minus because it's going to move in both directions, so it varies in terms of x. Then we want to find the exact position when the velocity is 2 centimeters. So the velocity then, when v is equal to 2, we substitute 2 in, and we get 2 squared. 9 minus 1/9 of x squared gives us 5 equal to 1/9 of x squared, because we've subtracted and moved everything around. That gives us x squared must be 45, or x is going to be plus or minus root 3. And again, its exact position, velocity is 2. Well, its velocity is 2 centimeters. It's going to be in one of the two positions there. So there's the ideas on simple harmonic motion, moving between 2 points, using some of the other work we've done in the Extension 1 course, and especially with the acceleration in terms of x, so we can start to combine those types of questions. Adds a little bit of difficulty, but it just means we have to be careful what we're starting with and where we're going.